So, welcome to Chapter 2, which focuses on atoms, molecules, and ions. The start of the chapter begins with the development of the atomic theory and how we basically came to understand what we understand about matter. I want to move through this portion rather quickly. Hopefully, you had an opportunity to spend some time on this topic in your previous study of chemistry, but it is worth reviewing because many of Dalton's postulates, which formed his theory of his atomic theory, are still relevant. So we know that every element is made up of very small particles that we call atoms. And we also know that all the atoms of a particular element are identical to one another, but atoms of different elements are different from each other, right? And then we also know that during a chemical reaction, the atoms themselves are not changed, but they are combined in different ways. So atoms are neither created or destroyed, but just merely rearranged to form new substances. Finally, we know that compounds are formed when atoms combine in a specific ratio. So, for example, hydrogen and oxygen combine in a ratio of 2 to 1 to form water. The other thing that's worth noting is that we have the law of constant composition, or also known as the law of definite proportion, which tells us that a pure substance always has the same composition. So water is always H2O. And finally, the law of conservation of mass, which tells us that the total mass that you have at the start of a chemical process is the same as the total mass that you have at the end. What do we know about the electron? Well, the electron was discovered fairly early because of its charge, and most of the study came about through the use of the cathode ray tube. Thomson is credited with discovering the electron. More information was later found out about the charge and the mass by Millikan and other scientists. Millikan's oil drop experiment, which is what allowed us to know the actual charge and the actual mass of the electron. So that's an important discovery as well. Radioactivity is not covered as part of chemistry at this stage, but it is important to understand that the changes are taking place in the nucleus, and it has to do with particles being given off by the nucleus. Okay, this was first observed by Henri Becquerel, and radioactivity was very useful. In fact, you might have heard of Marie and her husband Pierre Curie, who studied it, and unfortunately, sadly, Marie Curie passed away as a result of her exposure. Different types of radiation. You have alpha particles, beta particles, and gamma rays. For those of you who are studying particle physics, you know there are many more than these, but these are the ones that are relevant to us at this stage. The atom, or the structure of the atom, wasn't very well known around the 1900s, but based on Rutherford's experiment using alpha particles, we actually were able to find out more about the atom. If you recall the gold foil experiment, where by the use of alpha particles and the pattern of scatter of those alpha particles, he was able to actually figure out that the positive charge was concentrated in the core, a small nucleus we call it, and that's how we basically figured out that the nucleus exists. So that was a huge contribution for us. Finally, we did have the discovery of the neutrons. The neutrons took a lot longer to discover because they're neutral. Basically, they were able to figure that out based on the mass of the atoms, and something was missing. So just to summarize the subatomic particles, the proton, which is positive, the neutron, which is neutral and has pretty close to the same mass, and then the electron, which is negative and has a much smaller mass. And these masses that we're using are in AMU, which is atomic mass unit, which is a simplified unit that just allows us to work a lot easier with these very small masses. So we basically consider the mass of the electron to be negligible. It's so small that we ignore it. And the mass of the atom is just the total number of protons and neutrons. So if we wanted to represent a particular atom, we could use a symbol of the element, and then the atomic number, which is the number of protons, and for a neutral atom, that is the same as the number of electrons. And then you would have the mass number, which is the total number of protons plus neutrons. And given those two pieces of information, you can always determine the number of protons, neutrons, and electrons for a particular atom. Each element, or at least most elements, actually have variations in the number of neutrons, and those are referred to as isotopes. So isotopes are atoms of the same element with different mass numbers. And the reason why they have different mass numbers is because the number of neutrons are different. So you may be familiar with the fact that carbon has a variety of isotopes. The most common isotope is carbon-12, having 6 protons and 6 neutrons. But there's also carbon-13 and carbon-14. Carbon-14 is one that is actually used for radioactive dating, to actually figure out how old a living organism is. So different number of neutrons. So how do we determine these atomic masses? There's a mass spectrometer which takes a sample, use an ionizing beam to turn the particles in that sample into ions, and then a magnetic field will then deflect those particles. And the deflection, the amount of deflection depends on the mass. So now what you're able to do is separate the ions based on their masses, and then they're finally going to be detected, but because they did not get deflected the same amount, you end up figuring out how many, or the ratio of the different masses that you have. So what we use is actually an average mass. It's the weighted average of the masses of the isotopes. And you do need to be able to calculate that average given the percentage and the masses. So what do? We have the isotopic mass for each isotope, and you have the percentage. You multiply the percentage times the mass of each isotope, add those up, and divide by 100. That will give you the weighted average. Let's look a bit at the periodic table. Again, I'm moving relatively quickly, hoping that this is a review. It's a system that we use for cataloging the elements, the arrangement of which is very helpful in us to be able to predict the properties of many of those elements. The elements are arranged in order of atomic number from left to right. So in this periodic table, that's the number that appears above the symbol. And why do we call it a periodic table? It's because we notice a repeating pattern of properties when you put those elements in order by their atomic number. So the horizontal rows are referred to as periods. The vertical columns, top to bottom, there are 18 of those. Those are referred to as groups. And elements in the same group have the similar chemical properties. So that's the important relationship there. Now, the main group elements are known by some names. So group 1 is referred to alkaline metals, group 2 alkaline earth metals, etc. You should be familiar with these names as well. The nonmetals are located to the right of this zigzag line. So just be aware that this line here, the zigzag, separates the periodic table into metals and nonmetals. The one exception is that hydrogen, which is a nonmetal, is all the way on the left as element number 1. Along the border, which is that zigzag that I just referred to, is what we refer to as the metalloids or semi-metals. These are elements that have properties of both metals and nonmetals. Okay, there are 6 of those. And then finally, the rest of the elements are all metals. So there are many more metals in the periodic table, many more of the elements that are metals than nonmetals. Chemical formulas, hopefully this is quite familiar to you. You know it consists of letters and numbers. The letters represent the symbol for the element, and the number represents the number of atoms of that element that would be contained in one molecule of that compound. So you have molecular compounds that are nonmetals only. So as long as you have 2 or more different nonmetal elements combined, those are referred to as covalent compounds or molecular compounds, and you would represent those with a molecular formula. There are 7 elements that also exist as molecules naturally. You do need to know those 7. People use a variety of mnemonic devices. If you're a visual person, you might just remember this sort of upside down L and then hydrogen, or you can remember Hofbrinkel or have no fear of ice cold beer. There's a couple different tricks that you can use, but you need to know those 7. There are types of formulas. You have empirical formulas, which gives you the lowest whole number ratio of atoms of each element in a compound. So for example, H2O, that is the empirical formula and the molecular formula of water. But hydrogen peroxide, which has the formula H2O2, its molecular formula is H2O2, but its empirical formula would simply be HO. A structural formula is one that shows how those atoms are actually connected to one another. So you can draw methane in a variety of ways. You can represent it as a structural formula to show that carbon is in the middle bonded to the 4 hydrogen atoms with covalent bonds. You can also do what we call a perspective drawing, which shows that in 3 dimensions, one of those bonds is coming towards you and another one is going away from you. Ball and stick model would represent what you would get when you actually put the model together, and then the space filling model would represent how those electron clouds would actually occupy 3-dimensional space. Ions, so very important to recognize the pattern of what happens when atoms lose or gain electrons and become ions. The cations are positive, so the metals, when they lose electrons, become positive. Group 1, positive 1, group 2, positive 2, etc. And the anions are the nonmetals, what nonmetals refer to after they have gained electrons and become negative. So as a result of atoms losing and gaining electrons, you form what is known as ionic bonds, which is generally going to occur between a metal and a non-metal. You do not have molecules. You have each positive ion surrounded by negative ions and each negative ion surrounded by positive ion in what we call a lattice structure or crystal lattice structure. Simplest example, sodium chloride. Writing formulas for ionic compounds, you have to have a neutral formula. So you would do something which we call the crisscross method, where you would basically use the charges to determine the ratio of the ions. And so the charge of the cation would become the subscript of the anion without the symbol, and the charge of the anion would become the subscript of the cation. That formula needs to be represented as an empirical formula. These are some common cations